Okay, problem 2.6. Now we look at a continuous distribution, the exponential distribution. What are we asked to calculate in problem 2.6? They say, assume that a claim size x is exponentially distributed with parameter lambda. So what we assume is that x is exponentially distributed with parameter lambda, where lambda is 0.01. So we can just as well write 0.01 here, right? So assume that x is exponentially distributed with parameter lambda. And they say see problem 2.4 above. And the reason why they want you to see problem 2.4 above is because problem 2.4 tells you what the density should be in the case that you have an exponential distribution. And in problem 2.4, we see that if x is exponentially distributed, then the density of x is given by lambda multiplied by e to the minus lambda x. So in this case, it's 0.01 multiplied by e to the minus 0.01 multiplied by x. For x greater than 0, I think. And the for x greater than 0 part is important to remember. And the reason why it's important to remember is because when we calculate the mean of something, when we calculate the expected value of something, then we normally integrate the density over the entire real axis. And when we do that, we have to remember where on the real axis that the density is just equal to 0. So that's why the x greater than 0 part actually matters. Okay, so what do they say then? You know that your claim is between 10 and 100. So we know that x lies between 10 and 100. And it doesn't really matter if I use closed parentheses or open parentheses here because x is continuously distributed. And then they tell us that is all you know. So practically, we don't know that much. And then they ask, what is the expected value of the claim? Now, whenever you get one of these questions that tell you you know something about something, and then ask you for an expected value, then what you have to think right away is conditional expectation. So our goal is, we want to find the expected value of x, given what we know, which is given that x lies between 10 and 100. And for that, we can use the definition of conditional expectation that we have from page 18 in the book. So from page 18 in the book, we have that the mean of g of x, given that x belongs to A, is given by the mean of g of x restricted to A, so multiplied by the indicator function of x on A, and then divided by the probability of whatever we condition on, like that. Now, we also should recall probably that when we calculate the mean of g of x multiplied by an indicator, now what is the mean value of a continuously distributed stochastic variable? Well, in this case, it is given by the integral from minus infinity to infinity over g of x multiplied by the indicator function of x multiplied by the density f of x. Now, what can we see here? Well, one thing we can see is that the minus infinity to infinity boundaries should be replaced because the indicator function makes sure that the integrand itself is only different from 0 on the parts of the real axis that correspond to A. So what we do is we actually integrate over A and not the entire real axis. And this is the expression for the mean of g of x restricted to A. So it's essentially just you integrate g of x multiplied by the density on the set A. And we will use both of these to find the result in problem 2-6. Now, just before we close off this video, even though the goal is to find the mean of x given that x lies between 10 and 100, I would also like to just remind you guys that if x is exponentially distributed, with some parameter, then the expected value of x is given by what? Well, it is given by 1 divided by that parameter. So in our case here, the expected value of x is equal to 100. And what will be interesting to see is whether the conditional expectation of x, given that it lies between 10 and 100, whether that value is greater than or smaller than 100. Now, something kind of tells us that maybe that value should be smaller than 100, just based on the fact that we condition on the fact that x lies between 10 and 100, then it would be very, very weird if that value is exactly 100. But if we only knew that x could be between 0 and infinity, then the mean would be 100. But knowing that x can lie between 10 and 100, we should probably expect that x lies somewhere that's more between 10 and 100 than the value 100. So next video, we will start looking at the solution.